All right, buckle in. Number 10. Storegga Slide Megatsunami, 6200 BC. The seafloor didn't shake. A shelf of sediment the size of Iceland simply let go, and the land bridge between Britain and Europe vanished in minutes. The wave struck the Norwegian coastline at an estimated height of 12 meters. Within hours, the strip of land called Doggerland, a populated corridor of rivers, marshlands, and migrating herds, was gone. Not eroded over centuries. Removed. Swallowed in a single event. Around 6200 BCE, the Storegga Slide occurred off the western coast of Norway. An area of continental shelf, roughly 290 kilometers in length, collapsed in a submarine landslide of extraordinary scale. The displacement volume is estimated at 3,500 cubic kilometers of sediment, enough material to bury the United Kingdom under a layer 4 meters deep. That mass displacement generated a megatsunami that radiated outward across the North Atlantic basin, striking coastlines from Norway to Scotland to the Faroe Islands within hours. Geological surveys of coastal deposits in Norway, Scotland, and the Shetland Islands reveal sediment layers consistent with wave run-ups reaching 10 to 12 meters above contemporary sea level. In northeastern Scotland, tsunami deposits have been identified up to 80 kilometers inland, carried by surge channels that pushed far beyond the modern coastline. On the Shetland Islands, run-up heights may have exceeded 20 meters in confined coastal inlets, where the wave energy was concentrated by the shape of the terrain. The wave didn't merely flood coastlines. It reconfigured the geography of an entire region, redistributing millions of tons of sediment in a matter of hours, and leaving behind a stratigraphic marker that geologists still use as a reference horizon today. Doggerland, the land bridge connecting what is now Britain to the European mainland, had been shrinking for millennia as post-glacial sea levels rose steadily after the last ice age. What had once been a vast plain of grassland and wetland, home to human communities, had already been reduced to a narrow archipelago of islands and sandbanks. The Storegga Slide appears to have been the terminal event. Sediment cores extracted from the North Sea floor show a distinct layer of marine sand draped over what had been freshwater marshland and peat. The boundary is sharp, not gradual. The geological signature is one of sudden, violent inundation, a landscape overwritten in hours, its freshwater ecosystems replaced by saltwater in a single pulse. The slide itself was not a single failure. Seismic surveys of the North Sea floor reveal 3 distinct collapse events, each massive, occurring in rapid succession along the continental margin. The largest of these events alone displaced an estimated 2,500 cubic kilometers of material. The combined failure reshaped the seabed topography across thousands of square kilometers. The trigger remains debated among geologists. Leading hypotheses include gas hydrate destabilization, driven by warming ocean temperatures during the early Holocene, low-magnitude seismic activity along the continental shelf edge, or simply the accumulated weight of sediment on an oversteepened slope reaching a critical threshold. No consensus has been reached. Number 9. Missoula Glacial Lake Outbursts, 15,000 to 13,000 BCE. The same flood happened at least 40 times. Each one carried 10 times the flow of every river on Earth combined. And each time, an ice wall grew back and reset the clock. If you're not subscribed yet, now's the time. This list only gets heavier from here. The water was moving at 100 kilometers per hour. A wall of ice and debris, hundreds of meters high, tearing across the Columbia Plateau with enough force to rip basalt columns from the bedrock and carry them for miles. The landscape it left behind, a network of carved channels, barren scablands, and enormous boulder deposits, was so extreme that geologists refused to believe it was caused by water for decades. Glacial Lake Missoula formed during the last ice age when a lobe of the Cordilleran ice sheet advanced southward and blocked the Clark Fork River in what is now northern Idaho. Behind that ice dam, meltwater accumulated into a lake estimated at 2,100 cubic kilometers in volume, roughly the capacity of Lake Ontario. The lake stretched across 7,800 square kilometers of western Montana, its surface reaching depth of up to 600 meters at the dam face. The dam was not stable. Ice, unlike rock, floats. When the water pressure behind the dam reached a critical threshold, when the lake's depth exceeded roughly 60% of the dam's height, the ice began to lift. Water forced its way underneath, widening the channel, eroding the base, and within hours the entire structure collapsed. Lake Missoula drained in a matter of days. The flood that followed was catastrophic. Flow estimates place the discharge at 17 million cubic meters per second at peak velocity, approximately 10 times the combined flow of every river currently on the planet. The surge carved a path across eastern Washington, scouring the landscape down to bare basalt in places, creating the feature now known as the channeled scablands. It stripped topsoil to bedrock, excavated coulees up to 300 meters deep, and deposited house-sized boulders, known as erratics, across hundreds of kilometers of terrain. At Grand Coulee, the flood overtopped a ridge and carved an entirely new channel where no watercourse had existed before. At Dry Falls, a waterfall taller than Niagara and nearly 5 times as wide was formed and destroyed in the span of a single flood event. Then the ice returned. The glacier advanced again, reblocked the Clark Fork, and the lake refilled over a period of decades. The cycle repeated, at least 40 times over a period of roughly 2,000 years, according to sediment layer counts from the region. Each flood was a catastrophic reconfiguration of the landscape, erasing features carved by the previous event and replacing them with new ones. Each refilling was a countdown to the next one, a timer set by the rate of meltwater accumulation against the structural limits of an ice barrier. The evidence is scattered across the Pacific Northwest in the form of giant current ripples, sediment waveforms up to 15 meters high and 150 meters apart, visible from the air across the scabland terrain. These ripples are identical in structure to the ripples formed by water in a stream, scaled up by a factor of thousands. The boulder fields, the dry waterfalls, the stripped basalt, all of it points to a process that happened repeatedly, each event building on the destruction of the last. The mechanism that triggered these floods, an ice dam forming, a lake filling, a dam failing under hydrostatic pressure, is not unique to the Pleistocene. It operates wherever glaciers impound water on a slope. The conditions for another cycle exist wherever ice and topography align. The Missoula floods are not a singular event in Earth's history. They are a mechanism, and the mechanism is still available. Number 8. Late Devonian anoxic events, 372 to 359 million years ago. The oceans didn't warm, they didn't acidify, they simply stopped breathing, and 75% of all marine species suffocated in water that looked exactly the same on the surface. The first sign was the color. Black shale, dense, organic-rich, anoxic began appearing in marine sediment records across every major ocean basin, layer after layer spanning millions of years. Below the surface, the water column had stratified. Oxygen was no longer circulating to the deep. Everything that depended on it died. The Late Devonian was not a single extinction event. It was a series of extinction pulses spanning roughly 13 million years, clustered between 372 and 359 million years ago. The two most severe pulses, the Kellwasser events at the Frasnian-Famennian boundary, are associated with widespread oceanic anoxia. Marine fossil records from this interval show a steep, sustained decline in biodiversity. Reef-building organisms, which had dominated shallow marine ecosystems for millions of years, collapsed almost entirely. The tabulate stromatoporoid reef systems that had structured Devonian seas did not recover. The mechanism driving the anoxia remains under investigation. One leading hypothesis centers on the expansion of land plants during the Middle to Late Devonian. As vascular plants colonized the continental interior for the first time, they accelerated the weathering of silicate rocks on a massive scale. The products of that weathering, nutrients such as phosphorus and iron, were flushed into the oceans via river systems. This nutrient influx triggered eutrophication, massive algal blooms in surface waters that, upon dying and sinking, consumed the available oxygen as they decomposed. The deeper waters went anoxic. The process, once initiated, was self-reinforcing. A second hypothesis points to volcanic activity. Large igneous province eruptions in what is now Eastern Europe and Siberia released pulses of carbon dioxide and other gases during the late Devonian, warming the climate and reducing the solubility of oxygen in seawater. Warmer surface temperatures also increased the density difference between surface and deep water layers, strengthening stratification and preventing oxygen from reaching the bottom. Both mechanisms, nutrient-driven eutrophication and volcanic warming, may have operated simultaneously. The biological consequences were severe and uneven. Marine organisms in tropical, shallow-water environments suffered the highest extinction rates. Brachiopods, ammonoids, trilobites, and conodonts all experienced significant losses. The placoderm fish, heavily armored predators that had been the apex species of Devonian seas, were nearly eliminated. Organisms that could tolerate low oxygen conditions or that inhabited oxygenated surface layers fared better. But the overall marine biodiversity curve shows a sustained collapse from which recovery took millions of years. The black shale record from the late Devonian is global. It appears in sediment cores from North America, Europe, Asia, and Australia, in deep basins and shallow shelves alike. The same signature, dark, laminated, organic-rich sediment with no evidence of bottom-dwelling life, repeats across continents and ocean basins. The shale layers are often bounded by normal marine sediment above and below, indicating that anoxia came and went in pulses, each one lasting tens to hundreds of thousands of years. Whatever caused the anoxia, it was not local. It was a planetary-scale reorganization of the ocean-atmosphere system. The oceans recovered. They always do. But the recovery took longer than the extinction itself, millions of years of low diversity, simplified ecosystems, and slow reoxygenation. The anoxic events of the late Devonian are not the only times Earth's oceans have suffocated. Similar black shale events have been identified at other extinction boundaries. The conditions that produce them, nutrient overload, warming, stratification, are not confined to the deep past. They are observable today in the expanding dead zones along continental margins, where oxygen levels are already falling. Number 7. Campi Flegrei supereruption, 39,000 years ago. The eruption didn't form a mountain. It erased one. When Campi Flegrei erupted, it left a caldera 13 kilometers wide and may have helped eliminate the last Neanderthal populations in Europe. The ground dropped, not by meters, by hundreds of meters. An area of roughly 150 square kilometers in what is now the Campi Flegrei region west of Naples collapsed into the void left by a magma chamber that had emptied itself in a single, sustained paroxysm. The eruption column is estimated to have reached 40 kilometers into the atmosphere, punching through the troposphere and into the stratosphere. Ash blanketed the Mediterranean. The sky over southern Europe darkened for weeks. Temperatures dropped. The Campi Flegrei supereruption, dated to approximately 39,000 years ago, is one of the largest volcanic events of the late Pleistocene. It produced the Campanian ignimbrite, a sheet of welded ash and pumice covering more than 30,000 square kilometers across Italy and the Western Balkans. The deposit volume is estimated at 300 cubic kilometers of dense rock equivalent. That is enough material to coat the entire Italian peninsula in a layer of tephra, nearly a meter deep. The ash layer, known as the Y5 tephra marker, has been identified in marine sediment cores across the eastern Mediterranean and in terrestrial deposits as far east as the Black Sea. It serves as a stratigraphic reference point, a geological timestamp used to correlate archaeological and paleoenvironmental records across the region. The timing is significant. The eruption coincides with a period of rapid climatic fluctuation known as a Heinrich event, a cold phase during which massive armadas of icebergs calved from the Laurentide ice sheet into the North Atlantic, disrupting ocean circulation and lowering temperatures across Europe. The Campi Flegrei eruption injected sulfate aerosols into the stratosphere at precisely the moment the climate was already deteriorating. Proxy records from Greenland ice cores and European lake sediments show a sharp cooling spike around this interval. The combined effect of volcanic winter and glacial advance would have placed extreme pressure on the ecosystems of southern Europe, compressing habitable zones, shortening growing seasons, and reducing the productivity of both marine and terrestrial food sources. Neanderthal populations were already in decline by 39,000 years ago. Their range had contracted to refugia in southern Iberia, Italy, and the Balkans. Archaeological evidence suggests their population density had fallen to levels that may have been insufficient for long-term genetic viability. The eruption did not eliminate them single-handedly. The fossil record shows Neanderthal presence persisting after the event in some locations, particularly in southern Iberia. But the environmental degradation caused by widespread ashfall, acid rain, vegetation collapse, and rapid cooling would have fragmented their habitat and disrupted the food webs they depended on. Herds of grazing animals, the primary protein source for Neanderthal groups, would have been displaced or reduced by the destruction of pasture land. Genetic evidence suggests Neanderthal populations were already below viable replacement levels. The eruption may have been the stressor that pushed them past recovery, a single event that converted a slow decline into a terminal one across much of their remaining European range. The caldera that remains, the Campi Flegrei, is still active. Ground deformation, seismic swarms, and fumarolic activity have been recorded for centuries. The most recent episode of uplift, beginning in 2005, raised the port town of Pozzuoli by nearly 40 centimeters over the following decade. The system is monitored continuously by the Osservatorio Vesuviano and international research teams. The magma chamber beneath it is not empty. Seismic tomography reveals a partially molten body at depths of 7 to 10 kilometers. The question of whether it is recharging toward another eruptive threshold remains open and actively debated among volcanologists monitoring the region today. What is not debated is that a repeat of the 39,000-year-old event would place more than 1 million residents inside the caldera directly in the blast zone. Number 6. Lake Agassiz drainage event, 8,200 years ago. The lake held more water than every lake on Earth combined. When the ice dam gave way, it poured into the North Atlantic fast enough to shut down the ocean's heat engine, and global temperatures dropped 4 degrees within a decade. The freshwater hit the North Atlantic like a blade to the spine of the ocean's circulation system. Within years, possibly within a single season, the conveyor that carried warm surface water northward and returned cold deep water south had stalled. The result was the 2-kiloyear event, the most abrupt and severe cold snap of the entire Holocene, recorded in ice cores, lake sediments, and cave deposits across every continent. Glacial Lake Agassiz was the largest freshwater body North America has ever held. Formed by meltwater trapped behind the retreating Laurentide ice sheet, it covered portions of what is now Manitoba, Ontario, Saskatchewan, North Dakota, and Minnesota at its maximum extent. At its peak, it held an estimated 163,000 cubic kilometers of water, more than all the freshwater lakes on Earth today combined. The lake's outlet shifted repeatedly as ice margins retreated and re-advanced, each shift redirecting enormous volumes of water across different drainage basins. But the final drainage, is the one that rewrote the climate record. Around 8,200 years ago, the final remaining ice dam, likely located near the southern margin of Hudson Bay, collapsed. The lake drained in a pulse that is estimated to have discharged between 100,000 and 200,000 cubic kilometers of freshwater into the North Atlantic and Hudson Bay over a period of months to years. The precise duration of the discharge remains debated. Some models suggest a single catastrophic flood lasting weeks, while others favor a more prolonged release over several years. Regardless of the timescale, the influx of low-density freshwater capped the surface of the North Atlantic, preventing the formation of dense, cold, saline water that drives thermohaline circulation, the system that transports equatorial heat to the northern latitudes, the same system that today keeps Western Europe significantly warmer than comparable latitudes in Canada, was disrupted. The climate response was immediate and global. Greenland ice cores show a temperature drop of approximately 5 to 8 degrees Celsius within a few decades. Oxygen isotope records from the GISB-2 core reveal a sharp, sustained shift that lasted roughly 160 years before temperatures recovered to pre-event levels. Lake sediment records from Europe, North America, and East Africa show simultaneous cooling and aridity. In Central Africa, lake levels dropped markedly. In the Middle East, early agricultural settlements contracted, with archaeological evidence showing population dispersal from established sites during this interval. Pollen records from Northern Europe show a rapid return of cold-tolerant species at the expense of deciduous forests that had been expanding for thousands of years. Monsoon systems that fed the rivers of North Africa and South Asia weakened, and aridity expanded across the subtropics in patterns consistent with a weakened overturning circulation. The drainage of Lake Agassiz was not the sole cause of the 8.2-kiloyear event. Solar variability and other forcings likely contributed, but the timing and magnitude of the freshwater pulse align closely with the onset of cooling in multiple independent proxy records. Climate models that simulate a sudden discharge of Agassiz-scale freshwater into the North Atlantic consistently produce a weakening of the meridional overturning circulation and significant northern hemisphere cooling, matching the geological evidence with reasonable fidelity. The ice dam that held Lake Agassiz no longer exists, but the thermohaline circulation it disrupted still operates. The same mechanism, a sudden influx of freshwater into the North Atlantic capping the formation of deep water, remains one of the identified tipping points in the modern climate system. The freshwater sources have changed. Greenland melt, Arctic sea ice decline, increased precipitation at high latitudes. The physics have not. The 8.2-kiloyear event stands as the most recent proof that the ocean's heat engine can be knocked offline, and that when it falters, the atmosphere follows within years. Number 5. Krakatoa. The sun dimmed for 18 months. Crops failed from China to Ireland. And for over 1,000 years, no one could agree on what had caused it, until ice cores from both poles told the same story. The sky didn't darken for hours. It darkened for over a year. Across the northern hemisphere, written records from 536 CE describe a sun that was dim, blue-tinged, and cold, producing light without heat. Byzantine historian Procopius wrote that the sun gave forth its light without brightness, like the moon, during the whole year. Chinese chronicles record frost in July and failed harvests across multiple provinces. Irish annals describe a failure of bread, persisting from 536 through 539. Tree ring records from Ireland, Sweden, Finland, the United States, and Mongolia all show 536 as one of the coldest growing seasons of the last 2 millennia, a synchronized biological signature of planetary cooling. The cause was a massive volcanic eruption, or a sequence of eruptions, that injected sulfate aerosols into the stratosphere, where they circulated globally, scattering incoming solar radiation and reducing surface temperatures across both hemispheres. Ice cores from Greenland and Antarctica both show large sulfate spikes dated to approximately 536 CE, confirming a tropical or low-latitude eruption of extraordinary magnitude. The sulfate deposit in the Greenland GISB2 core ranks among the largest of the entire Holocene. The specific volcano responsible has been debated for decades. Candidates have included Krakatoa in the Sunda Strait between Java and Sumatra, Ilopango in what is now El Salvador, and an unidentified Icelandic or Alaskan volcano. Recent high-resolution ice core analysis and tephra shard matching have pointed increasingly toward Ilopango as the primary source of the 536 sulfate signal, though the case remains open, and some researchers still argue for a multiple eruption scenario. Regardless of which volcano produced the initial blast, the atmospheric consequences are unambiguous in the proxy record. The cooling was severe and prolonged. Global average temperatures are estimated to have dropped by 1 to 2 degrees Celsius, enough to shorten growing seasons across the northern hemisphere by several weeks and to reduce precipitation in monsoon-dependent regions. In Scandinavia, tree rings show almost no growth for 2 consecutive years. In the Americas, drought conditions intensified across the Yucatan Peninsula and the southwestern United States, with lake-level records from Mexico showing a marked decline. In China, snow was reported in August. The cold persisted through 537 and into 538, with some proxy records suggesting a secondary eruption or continued aerosol loading extending the climate impact for nearly a decade. The societal consequences cascaded across continents. The Byzantine Empire, the Sassanid Empire, and the kingdoms of the Arabian Peninsula all experienced crop failures, famine, and population stress during the late 530s. Archaeological and textual evidence suggests that the weakened populations of the Mediterranean and Near East were then struck by the first pandemic of bubonic plague, the Plague of Justinian, which erupted in 541 CE. The connection between the volcanic winter and the subsequent plague is not causal in a direct sense, but the malnutrition, displacement, and compromised immune systems that followed years of failed harvests would have created conditions in which a novel pathogen could spread rapidly and lethally through densely packed, undernourished populations. The 536 event was not the largest eruption of the Holocene, but it is the best documented volcanic winter in human history, the first time a global climate shock from a single eruption can be traced through written accounts, biological proxies, and atmospheric chemistry simultaneously. The sulfate aerosols eventually settled. The atmosphere cleared. The sun returned to its normal brightness. The volcanic source, whatever its identity, left behind a caldera, a collapsed void where a mountain had stood. The mechanism that produced the dimming is still active. A repeat of a 536 scale eruption would not require a super-eruption. It would only require a stratospheric injection large enough to circulate globally. That threshold is lower than most assume, and the next eruption to cross it is not a question of if, but when. Number 4. The Great Oxygenation Event, 2.4 billion years ago. The organism responsible didn't evolve to kill anything. It simply exhaled, and that exhalation wiped out the dominant life forms on the planet for the next billion years. The poison was oxygen. For the first 2 billion years of Earth's history, the atmosphere contained almost none of it. The planet's air was a mixture of nitrogen, carbon dioxide, methane, and water vapor, reducing gases that supported the metabolism of anaerobic organisms that had colonized every niche from deep-sea hydrothermal vents to shallow tidal pools. These organisms were not a marginal presence. They were the biosphere. Every biochemical cycle, every metabolic pathway, every ecological structure on the planet was built around the absence of free oxygen. Then cyanobacteria evolved oxygenic photosynthesis. The mechanism was elegant, split water molecules using sunlight, extract the hydrogen for energy, and release the oxygen as waste. The organism didn't need the oxygen. It didn't use it. It simply dumped it, a metabolic byproduct, exhaled into an environment that had no capacity to absorb it. For hundreds of thousands of years, possibly millions, the oxygen didn't accumulate. It reacted with iron dissolved in the oceans, with sulfur compounds, with organic matter, consumed by chemical sinks as fast as it was produced. The geological record preserves this process as banded iron formations, layers of iron oxide deposited on the ocean floor. Each layer a record of oxygen reacting with dissolved iron and precipitating out of solution. These formations are among the most distinctive geological markers on the planet, found on every continent, and they represent the planet's first attempt to buffer the oxygen flood. Then the buffer saturated. The iron was consumed. The sulfur was consumed. The organic matter was consumed. And the oxygen, still being produced, still being exhaled by cyanobacteria across every sunlit surface of the planet's oceans, had nowhere left to go but up. It entered the atmosphere. The consequences for anaerobic life were catastrophic. Free oxygen is corrosive at the molecular level. It strips electrons from organic compounds, degrades proteins, and ruptures cell membranes in organisms that evolved no defenses against it. For anaerobic organisms, which constituted the overwhelming majority of life on Earth, the rising oxygen concentrations were lethal on a planetary scale. The geological record shows a sharp shift in biosignatures around 2.4 billion years ago. The isotopic fingerprints of anaerobic metabolisms decline, and the signatures of oxygen-dependent processes appear for the first time. The transition is not gradual. It is a threshold event, a crossing. The oxygen also attacked the atmosphere itself. Methane, a potent greenhouse gas that had helped maintain surface temperatures above freezing during the Archean Eon, when the sun was 25 to 30% dimmer than it is today, was oxidized to carbon dioxide and water. The loss of methane triggered a planetary cooling event known as the Huronian glaciation, one of the longest and most severe ice ages in Earth's history. Glacial deposits from this period have been identified on every continent, including near the equator, suggesting that ice may have reached tropical latitudes. The planet may have frozen over entirely, a snowball Earth scenario, driven not by an asteroid or a volcano, but by the waste product of a single-celled organism. The organisms that caused the extinction didn't die. Cyanobacteria survived. They are still present in every ocean, every lake, every moist surface on the planet. They are among the most successful organisms in the history of life. The oxygen they produced didn't just kill. It opened an energy pathway, aerobic respiration, that yields far more ATP per unit of fuel than any anaerobic process. The oxygen they poisoned the world with became the foundation for every complex, energy-hungry organism that followed. The Great Oxygenation Event was the first mass extinction, and the first biological reengineering of an entire planet's atmosphere. The cyanobacteria that caused it are still here. They are still exhaling, and the atmospheric oxygen concentration they established, roughly 21%, remains the chemical environment that every animal on Earth depends on to survive. Number 3. Siberian traps flood basalts, 252 million years ago. The lava didn't erupt from one volcano. It bled from the ground across an area the size of the continental United States, and it kept bleeding for 300,000 years. The ground didn't explode. It opened. Across a region estimated at 7 million square kilometers of what is now central Siberia, fissures in the crust released a continuous flood of basaltic lava, not from a single vent, but from a network of channels that spread across the landscape like cracks in a shattered windshield. The Siberian traps were not a volcanic event. They were a volcanic province, an eruption so distributed, so sustained, that it redefined the boundary between a disaster and a geological epoch. The total volume of magma released is estimated at between 2 and 4 million cubic kilometers, enough to cover the entire continental United States in a layer of basalt over a kilometer deep. The eruption persisted for an estimated 300,000 to 500,000 years, with the most intense phase concentrated in a much shorter interval at the outset, possibly as brief as 60,000 years. The lava itself was destructive on contact, incinerating everything it touched, filling river valleys, burying ecosystems under successive flows. But the lava was not the primary killer. The gases were carbon dioxide, sulfur dioxide, halogens, chlorine, fluorine, bromine, and potentially vast quantities of methane were released in volumes that overwhelmed every atmospheric and oceanic buffer system on the planet. Carbon dioxide concentrations in the atmosphere are estimated to have increased by several thousand parts per million over the eruptive period, driving global temperatures upward by 8 to 14 degrees Celsius in some model estimates. Sulfur dioxide produced acid rain on a scale sufficient to strip vegetation from continents and acidify surface waters. Halogens degraded the ozone layer, increasing ultraviolet radiation reaching the surface. Methane, possibly released from permafrost thawing, from methane clathrate deposits on continental shelves destabilized by warming oceans, or from carbon-rich sediments heated by the intrusion of magma into the crust, amplified the warming further. The oceans absorbed a significant fraction of the carbon dioxide, driving down pH and reducing the availability of carbonate ions that marine organisms use to build shells and skeletons. Ocean acidification, combined with rising temperatures and expanding anoxic zones, devastated marine ecosystems. Reef systems that had persisted for millions of years collapsed. The isotopic record from marine carbonates shows a sharp negative excursion at the Permian-Triassic boundary, a signal consistent with a massive injection of light carbon into the ocean atmosphere system, exactly the signature expected from a prolonged, CO2-rich eruption. Siberian traps are the leading candidate for the primary trigger of the Permian-Triassic mass extinction, the most severe biological crisis in the fossil record, in which an estimated 96% of marine species and 70% of terrestrial vertebrate species were lost. The timing is exact. The most intense phase of Siberian traps volcanism, as dated by radiometric methods, aligns precisely with the Permian-Triassic boundary at 252 million years ago. The mechanisms, warming, acidification, anoxia, ozone loss, match the extinction patterns observed in the fossil record across both marine and terrestrial environments. The magma source was a mantle plume, a column of abnormally hot material rising from deep within the Earth's mantle, burning through the crust and releasing its load of molten rock and dissolved gas over hundreds of thousands of years. That plume has not been repeated at this scale since. But the mechanism, mantle plume eruption, flood basalt release, greenhouse gas overload, is not unique to the Siberian traps. Similar, smaller events have occurred. The Deccan traps in India, the Central Atlantic Magmatic Province, the Ontong Java Plateau, each is associated with a biotic crisis. The Siberian traps are simply the largest and the most lethal. The conditions that produced them, a hot mantle plume intersecting volatile-rich crust, exist elsewhere in the Earth's interior today. The next one is not being monitored. There is no monitoring system for it. At number 2, Chicxulub asteroid impact, 66 million years ago. The asteroid struck at 20 kilometers per second. The energy released was equivalent to 100 million megatons of TNT, and the first thing to die was the ground itself. The rock hit the shallow sea covering what is now the Yucatan Peninsula at an estimated angle of 45 to 60 degrees. On contact, the impactor, roughly 10 kilometers in diameter, vaporized itself, and a significant volume of the target rock, generating a fireball that expanded outward at velocities exceeding the speed of sound. A crater 180 kilometers wide and 20 kilometers deep was excavated in seconds. The rim collapsed inward within minutes. The blast wave flattened forests within a radius of 1,500 kilometers. Anything within that zone that could burn, burned. The Chicxulub impact, dated to 66 million years ago, marks the Cretaceous-Paleogene boundary, the geological horizon at which the non-avian dinosaurs, along with approximately 76% of all species on Earth, disappeared from the fossil record. The impactor was likely a carbonaceous chondrite asteroid, though a comet has not been entirely ruled out. The energy released on impact is estimated at 4 times 1023 joules, roughly a billion times the energy of the Hiroshima bomb. The immediate effects were devastating within a hemispheric radius. Thermal radiation, blast overpressure, earthquakes exceeding magnitude 10, and tsunamis with wave heights estimated at 100 to 150 meters striking the coastlines of the Gulf of Mexico and the Atlantic. But the global extinction was driven by what followed. The impact ejected massive quantities of pulverized rock, sulfate minerals, and soot into the stratosphere, where they circled the planet for years. Sulfate aerosols scattered incoming sunlight, reducing surface temperatures by an estimated 10 to 20 degrees Celsius globally and cutting photosynthesis to a fraction of its normal rate. The food chain collapsed from the base up. Soot from global wildfires, ignited by the thermal pulse and confirmed by charcoal layers in the geological record at multiple sites, amplified the darkness. Ocean surface productivity crashed. The carbonate compensation depth in the oceans shallowed, dissolving the shells of marine organisms that relied on calcium carbonate. The recovery interval, the time required for biodiversity to return to pre-extinction levels, is estimated at 4 to 10 million years. The non-avian dinosaurs never returned. The ecological niches they vacated were eventually occupied by mammals, a group that had existed in the dinosaurs' shadow for over 100 million years, but had never grown larger than a badger. The impact didn't just end a dynasty, it opened one. The crater is buried under a kilometer of sediment. It was not identified until 1978, when geophysicists searching for oil noticed a gravitational anomaly in the Yucatan. The asteroid that made it was not detected before it arrived. No system existed to detect it. The asteroid that strikes next will not be detected by the dinosaurs' infrastructure. It will be detected by ours, or it won't be detected at all. Number 1. Permian-Triassic extinction, 252 million years ago. It killed 96% of all marine species. The extinction itself may have unfolded in under 60,000 years, but the recovery took 30 times longer, and the world that came back was not the one that died. The seafloor went silent. The fossil record across the Permian-Triassic boundary shows a near-total cessation of bioturbation, the burrowing, feeding, and sediment-disturbing activity of bottom-dwelling organisms. For millions of years before the boundary, the seafloor had been reworked continuously by worms, arthropods, and other infauna. After it, the sediment is undisturbed, laminated, empty. The bottom of the ocean had become a dead zone. The Permian-Triassic extinction, the Great Dying, is the most severe biological crisis in the history of life on Earth. Occurring 252 million years ago, it eliminated an estimated 96% of all marine species and 70% of terrestrial vertebrate families. In the oceans, reef ecosystems that had persisted for tens of millions of years collapsed entirely and did not reappear for 8 to 10 million years. Trilobites, a group that had survived 4 previous mass extinctions over 270 million years, vanished completely. Brachiopod diversity crashed by over 80%. Fusulinid foraminifera, which had been among the most abundant shelled organisms in Permian seas, were entirely eliminated. On land, the extinction was equally severe. Plant communities across what is now the Siberian region, China and Gondwana, show a sharp shift from diverse assemblages to assemblages dominated by a single genus. the opportunistic fern dicroidean in some regions, or the spore-producing quillwort in others. Vertebrate fossil records from the Karoo Basin in South Africa show a collapse in species richness and body size across the boundary, with large herbivores and apex predators disappearing and remaining fauna dominated by small, generalized survivors. Coal deposits, which form from the accumulation of organic plant material in wetlands, disappear from the geological record for roughly 10 million years after the boundary, a phenomenon known as the coal gap. The ecosystems that produced peat and coal did not exist. They had to be rebuilt from zero. The kill mechanisms were multiple and synergistic. The Siberian Trap's eruptions injected massive volumes of carbon dioxide and sulfur dioxide into the atmosphere, driving rapid warming, acid rain, and ocean acidification. Warming of 8 to 14 degrees Celsius increased the thermal stratification of the oceans, reducing oxygen delivery to deep waters and expanding anoxic zones. Evidence from biomarker molecules, specifically traces of green sulfur bacteria, which require both anoxic conditions and light, indicates that hydrogen sulfide accumulated in the upper water column, reaching depths where photosynthesis was still possible. The oceans were not just depleted of oxygen, they were actively poisonous. Hydrogen sulfide, if outgassed from the ocean surface, would have degraded the ozone layer, exposing terrestrial life to elevated ultraviolet radiation. Mutagenic UV levels would have compounded the effects of heat stress, drought, and habitat loss on land. The combined assault, warming, acidification, anoxia, toxicity, ozone depletion, created conditions that exceeded the physiological tolerances of the vast majority of organisms alive at the time. Not just the vulnerable. Not just the specialized, nearly all of them. The recovery was slow on a scale that is difficult to contextualize. Marine biodiversity did not return to pre-extinction levels for an estimated 8 to 10 million years. Terrestrial ecosystems took 15 to 30 million years to fully re-establish complex food webs. The world that recovered was not the world that had died. New groups dominated, old groups were gone, and the ecological architecture of the planet had been permanently altered. The Great Dying did not simply reduce the number of species. It reset the rules of what life could be. The mechanism that caused it, massive volcanic greenhouse gas release driving warming, ocean anoxia, and cascading ecosystem collapse, is not locked in the deep past. The quantities of carbon dioxide emitted by the Siberian traps over hundreds of thousands of years are comparable in terms of rate to the quantities being emitted by human industrial activity today. The speed is different. The chemistry is the same. The ocean is currently acidifying. The anoxic zones are currently expanding. The temperature is currently rising. The experiment is being run again, not by a mantle plume, but by a species that emerged in the aftermath of the last one.